Hello everyone. In the second lecture of solid state chemistry, our today's topic of discussion are assignment of atoms per unit cell, close packing, and maximum volume occupation in a cube for primitive face-centered cube and body-centered cube. In this context, let's start with assignment of atoms per unit cell. Assignment of atom means you are given some space lattice. Now, some atom is placed in any part of that space lattice. It may be in its body center, it may be in its face center, or it may be in its edge center, which is actually not usual. But somehow, if provision comes, then we shall discuss about that. If it exists in the vertex, then how many part of that sphere or that motif is inside that unit cell and how many part is outside that unit cell. So the part which is inside the unit cell is actually the number of atoms assigned per unit cell. Okay, so let us elaborate by taking an example of a sphere which is being cut into pieces. First, along this line, it is cut into two pieces, two equal hemispheres. So it becomes half. On further cutting it into two, it becomes 1/4. And finally, when you cut it into equal two pieces again, then it results in 1/8 of that sphere. Now let us check in which examples these are found. If it is a body-centered space lattice, then the whole part of the sphere is inside the unit cell. And these types of examples are found in body-centered cubes such as BCC. Okay, then the number of assignment is 1. That is, the full atom is inside the unit cell. If it is in the face center, then half is inside the unit cell and half is outside. So half number of atom is assigned here. So in the face centers or the center of face, half number of atom is inside the unit cell. If somehow, say, it is in the center of the edge, okay, then 1/4 of it is inside and 3/4 is outside. So in that case, in the center of edge, 1/4 is inside, assigned inside. So these types of examples are found in case of the cations in an anionic face-centered cubes, for example NaCl. Okay, so the vertex are occupied by the chloride ions, while the Na plus ion, that is the cations, are occupying the edge centers, that means in between the two vertex. Okay, so these types of examples are found in case of sodium chloride. And finally, if you place the sphere in the vertex, then only 1/8 part is assigned inside and 7/8 part is outside. So this is generally found in the primitive cases and on all other cases also where there is a vertex. There is the sphere is the vertex. Okay. So if you count the whole number of atoms assigned inside the unit cell, then in case of primitive you will get 1. How? 1/8 is inside. There are total 8 number of vertex. So 8 into 1/8 equal to 1. In the face center, 1 is contributed from the vertices and remaining 3 is contributed from the 6 faces. Each face is contributing half. So 6 faces are contributing 3. So 3 plus 1 is 4. In the body-centered cube, 1 is completely inside and 1 is contributed from the vertices, so 2. In case of C-face centered space lattice, 1 is contributed from the vertices and half is contributed from the top face, while the half is contributed from the bottom face. That is 1 plus half equals to 2. So these are the elaboration for primitive 1/8 from the vertices or the corner or the apex. Total number of apices are 8, so total number of atoms inside the cube is 8 into 1 by 8 equals to 1. In case of face centered cube, 1/8 into 8 contributed from the vertices and half into 3 contributed from the face centers. Okay, so overall number is 4. In case of body centered cube, 1 is contributed from the vertices and 1 is contributed from the body center. So overall 2 are assigned inside the BCC space lattice. Finally, the C-face centered space lattice has 2 assigned inside. Okay, so these are all written here. 1/8 into 8, half into 2, so 1 plus 1 equals to 2. Now moving to the next topic, which is close packing. Here in the space lattices you find that the motifs or the lattice points are maintaining some distance. They are not in contact with each other. So if they are compressed and made to come closer and closer, then at some time they will come into contact with each other, and that type of crystal structure is called a close packed crystal structure or close packing simply. So if it is in the closely packed form, then what is the maximum percentage of volume which is occupied by the spheres or the or the lattice points? So when the lattice points are in closest contact with each other, then it's called close packing. For a face-centered space lattice, its close-packed structure is also known as the cubic close-packed structure, or in short CCP. This part would be discussed at the time of tetrahedral void and octahedral void, not now. Next, it can easily be calculated that a simple cube has 52.3% maximum volume occupation. A cubic close-packed, that is a closely packed face-centered cube, has 74% maximum volume occupation, and a BCC space lattice, which is when in close packed system, then this lattice has 68% maximum volume occupation. So let's start with the primitive cube or the simple cubic system. So this is the partial view of a closely packed cubic system or a CCP. Partial view means it's a two-dimensional view. Okay. So if you take only two-dimensional view, then one of its face or surface would look like this picture. Here in this picture, this point to this point has the distance of A, which is actually the edge length, and its half distance is actually the radius of each sphere. So let's start. A is therefore twice R, because half of A is R, then another half of A is another R, so A is actually twice R. That means R equals to A by 2. Now volume of each sphere is 4 by 3 pi r cube. Now if you put a by 2 instead of r, then you can get the volume of each sphere in terms of edge length a. So we are putting here a by 2 in place of r. So it becomes 4 by 3 pi a by 2 whole cube. That gives the result pi by 6 a cube. Now in a primitive space lattice, you have only one atom inside the cube. So the occupied volume is actually 1 into pi by 6 a cube. This is the occupied volume. 1 means one number of atoms is inside, and each atom has the volume in terms of a has pi by 6 a cube. So finally the occupied volume is also pi by 6 a cube. Now try to find out what should be the volume of the cube in terms of a. If a is the edge length and if it's the cube, then its volume should be a cube. So the volume of the unit cell is a cube. So out of this overall a cube volume, the amount of occupied volume is pi by 6 a cube. Then the fraction of occupied volume is pi by 6 a cube over a cube. And the percentage of occupied volume is that fraction into 100%. That gives the result 52.3. So it is the lowest volume occupancy, and so the highest void space, which is 47.7%. Now let us calculate the maximum volume occupation for a HCP. That means hexagonal close packed, that is closely packed face-centered cubic space lattice. Now this is another partial view or the top view or the two-dimensional view, where the distance between this point to this point is a, but this a this time is not twice r. Why? Because here these two spheres are not touching each other. Which spheres are touching each other? Along the diagonal, this sphere is touching this sphere, which is further touching this sphere, and the distance between the center of the two extreme spheres is actually 4r, which is in turn the diagonal of the cube, or here in this top view of the square, diagonal of the square. So what is the diagonal of a square? If a is the side length or edge length, then its diagonal is a root 2. So a root 2 is equal to 4r. So you can express r in terms of a as a root 2 by 4, that is a by twice root 2. So this is the relationship between r and a. So volume of each sphere 4 by 3 pi r cube is actually 4 by 3 pi a by twice root 2 whole cube. That gives the result pi by 12 root 2 a cube. So this is the volume of one sphere in terms of a. Now how many spheres are inside that cubic space lattice, that is face-centered cubic space lattice? There are now 4 number of atoms assigned. So we have to multiply this volume by 4. If you multiply this volume by 4, then you will get the overall occupied volume, which is actually pi by 3 root 2 a cube. Now what is the overall volume of the cube of the unit cell? Which is actually a cube. So the fraction is pi by root 3 a cube divided by a cube. This is the fraction of volume occupancy. So if you multiply this by 100, then you will get the percent occupation or the percent occupancy, which is actually 74%, which is the highest volume occupation. So the void space is lowest, which is 26%. Now finally, let us calculate the volume occupation in a body-centered cubic closed packed system. Here you have to draw a partial view. Okay, overall there are 8 vertices and 1 body center, so there are 9 lattice points, but we have to draw 3 lattice points which are in contact with each other along the volume diagonal of the cube. Okay, and this time this volume diagonal is a root 3. Okay, this a root 3 is actually 4r. So volume diagonal is a root 3 equals to 4r, or r in terms of a is 4r divided by root 3. I'm sorry, a root 3 by 4. A root 3 by 4. So we get the relationship between r and a. Now volume of each sphere, that is actually 4 by 3 pi r cube. Instead of r, when you write a root 3 by 4, then you will get the value pi root 3 by 16 a cube. Now volume of each, actually number of atoms within the body centered cube assigned is 2, because 2 atoms are within the body centered cubic space lattice. So it should be multiplied by 2 in order to get the overall volume occupancy. So we are multiplying by 2 to get the value, final value, pi root 3 by 8 a cube. So if it is divided by the volume of the cube a cube, then you will get the fraction of volume occupation. And if you multiply this by 100, then you will get the percent occupancy of volume. And if you subtract this from 100, then you will get the void space. So the volume occupancy is 68% and the void space is 32%. So the HCP, or the face centered cubic closed packed system, is the highest occupied closed packed system, which is actually 72%. Okay, so here is the summary. So FCC is the closest packed space lattice, which is 74% volume occupancy and 26% void space, and the lowest one is the primitive, which is 52.3% volume occupancy and 47.7% void space. In between there is the body centered cube, where is 68% volume occupied and 32% is unoccupied. So that's all for today. Thank you.